Hi everyone, welcome to the session on learning and tomography, and we will start the session with Anna Mele from Freie Universität Berlin, and he will talk about learning and testing quantum states of fermionic systems. Take it away.
Thank you, Jonas. And can you hear me? Sorry. Okay, try. Try. Okay. Okay. Try. Okay. Hello everyone, I am Antonio, and today I'm going to talk about learning and testing quantum states of fermionic systems. And this is a joint work with great collaborators, Lennart, Jens, Yaroslav, and Lorenzo. And the last three of them you can find here at QIP, also in this session. And please feel free to reach them after the talk also. And okay, in this talk I will first introduce what learning, testing means, and also what fermions are. Then I will talk about learning fermionic Gaussian states that are easy states, and then I will talk about learning more complex types of fermionic Gaussian states. And okay, let's start with an introduction. Advances in quantum technologies have inspired basically a new field called quantum learning, and this is basically studying what you can learn rigorously from quantum systems. And if you have followed the tutorial of Robert Wang on Saturday, you also have had a good motivation about this. And typical problems considered in this field are, for example, learning unknown quantum states, where you have a few copies of unknown states, and you want possibly to recover an efficient classical description of this unknown state. And without any prior information about the states that you have, this task is hard. It requires exponentially many copies of the known quantum state to be solved. However, if more assumption on which states you have, if you have an additional assumption, efficient learning might be possible. For example, you know that your state has a little entanglement, or is a stabilizer states, or it's a states prepared by Clifford gates and a few T gates, then tomography is efficient. Okay? And this is a problem considering this quantum learning field. And the second problem is testing properties of quantum states. Here, the task is to decide if an unknown quantum state is close or far from a given class. For example, is the state that I'm looking at a stabilizer state or far from being? Is this state close to be separable or far from being separable? This is basically testing. And okay, an important class of quantum states are fermions. And for those of you that are more from computer science, fermions are a type of quantum particle. This is the standard model of elementary particles, and there are fermions and bosons. And basically, fermions make up all the matter. And fermions, like electrons, are important in all quantum technologies of today. And they describe, for example, molecules. And many computational problems about designing materials and chemicals can be translated about fermionic problems. And this is basically the goal of many computational algorithms that today are run in classical computers, and hopefully we will have them running and solving problems also on quantum computers about fermions. So fermions are really important, and despite their importance, research on learning fermionic systems remain limited with a few works available. And yeah, in this presentation, I will talk about how we possibly try to push this boundary and give more works about learning and testing quantum state fermionic systems. We start with arguably the simplest class of fermionic states that are Gaussian states. I will talk more about their definition. And then we will look about more complex states that are so-called T-doped Gaussian states that are basically states prepared by Gaussian circuits that are easy circuits like Clifford, and few magic gates or interacting gates that are like magic fermionic gates. And we will show practical efficient algorithms for learning and testing these types of states in some scenario, and also show situations where any algorithm must be inefficient, probably. And along the way, we uncover also fundamental properties of interest of these two classes of states that might be interest also to the many-body physics community. Okay, this is the content of the first work, and this is the content of our second work that make this talk. Okay, so let me introduce fermionic Gaussian states that are types of states that in the literature are called in 1,000 different names. For example, they are also called free fermionic states, non-interacting fermion states prepared by 1D match gate circuits or linear optics, fermionic linear optic circuits. Yeah. For the purpose of this talk, I will define them like Gibbs states of free fermion simultaneans, and Gibbs states are these defined like this, where they depend by an Hamiltonian, and that is called free fermions. That is basically a quadratic Hamiltonian in some objects called Majorana operators. These can be defined like abstractly, independent by living in a qubit Hilbert space. But for the purpose of this talk, I will focus in qubit systems, since I assume most of you are familiar with qubits rather than fermions. And Majorana operators can be defined just some set of Paulis. They are just n different Paulis, and for example, can be defined in this form, also called Jordan-Wigner definition of Majorana operators. And an important concept is the notion of Gaussian unitaries, that is just the time evolution of free fermionic Hamiltonians. While Gaussian states are Gibbs states of free fermionic Hamiltonians, Gaussian unitaries are time evolution. And why studying Gaussian unitaries and states? Because they model interesting physics, like free fermions, free particle of fermions. And they are also models for many metals and semi and superconductors. And also they are very important because they are basically classically easy to simulate, and they are the center of exactly solvable model studied since a century in physics. And okay, and at the center of their classical simulation, there is an object called correlation matrix. It is a 2n times 2n object. And for example, it is called correlation matrix, and it basically called like this because it encodes the correlation, the two-body correlation of a quantum states, and is defined like this, the two-body in Majorana operators. And yeah, so encodes is an antisymmetric matrix that encodes just some Pauli expectation value. And yeah, as a stabilizer state is specified by its stabilizer generators, a free fermionic state is fully determined by its correlation matrix that encodes just few Pauli expectation values. So, how to learn fermionic Gaussian states? We have just said that they are fully determined by the correlation matrix. So we can just estimate this few Pauli expectation value and learn the state, right? But here we have to be careful because it's very important, the definition of learning, that is with a specific distance called trace distance or one norm. Basically, the definition of learning is that given n copies of a known state, in this case assumed to be Gaussian, the goal is to output ρ such that with high probability we have that these two states are in trace distance close. So if we estimate the correlation matrix, we associate it to a Gaussian state, we need to transfer this error to the norm difference of the Gaussian states. And we need norm bound between Gaussian states and their correlation matrices. So our first theorem is about this. Let ρ and ρ tilde be two Gaussian states, then this inequality holds. The trace distance between two Gaussian states is upper bounded by the norm difference of the correlation matrix. And this is the crucial idea for the performance of our learning algorithm, but this inequality can also be used in many body physics, and up to our knowledge was not known in the literature. And we also show a lower bound that does not depend by the assumption that the two states are Gaussian, this, and together they give also an operational meaning to the norm difference between correlation matrix of two Gaussian states, saying that their error is really the trace distance error. And for pure Gaussian states, if we have the pure assumption that states are pure, we can also tighten up these bounds. So this will be the one norm with the true norm of Frobenius norm that is tighter. And we show that these bounds are tight, are optimal in this functional dependence. They cannot be improved. Okay. And so we show that n to the alpha copies of the non-Gaussian state suffice to learn. And where alpha is 4 for possibly mixed Gaussian state, and 3 if we have the prior assumption that the states are pure. The state is pure. And this improves over previous state-of-art bound that was n to the 5, epsilon to the 4. We improve quadratically the number of modes of qubits dependence and also the accuracy. And the algorithm is just estimate the correlation matrix and regularize it and apply the previous bound that we showed. And the protocol is experimentally feasible, single copy, simple measurement, and noise robust, meaning that you don't need to assume that the state is exactly free fermionic. It's also enough to have the assumption that it is close enough in some metric to be free fermionic. Okay. Also, the second problem that we analyze is testing Gaussian states, unknown Gaussian states. We have some copy, we do some measurements, and we want to output or the state is close to big Gaussian or far from big Gaussian. And the problem can be formalized in this form. We have n copies, and we need to decide if the state is epsilon a close to big Gaussian. There exists a Gaussian state such that rho minus sigma is smaller than epsilon a, or epsilon b far from big Gaussian, meaning that for all state, rho is for all Gaussian state, rho is epsilon b far from b. Yes, this inequality also. And our first result is that testing Gaussianity is hard. We need an exponential number of copies to solve the Gaussian testing problem. And this automatically implies that there is no measure of fermionic magic which can be estimated efficiently, because if there was, then we can solve the Gaussian testing problem efficiently. And but what if the known state or the Gaussian set that we test to is assumed to have a bounded rank, like is assumed to be pure or whatever? Here we show omega r copies are necessary. And so a natural question is there an efficient algorithm in this regime? And we show that indeed there is an efficient algorithm under appropriate condition on epsilon a, epsilon b that are the two thresholds. Okay. These are our results concerning Gaussian states. Let me go to the last topic, that is the T-dot fermionic Gaussian states. And I will start with a quick introduction. Gaussian states, we've seen that they are efficient to classically simulate, and also are classically easy. They are easy to learn, unlike general quantum states that are hard to simulate, likely, and also hard to learn, probably. And how to interpolate between these states? Okay, here comes the notion of T-dot Gaussian states that are just states prepared by Gaussian unitaries and few T fermionic magic gates that are defined like so-called K-mode non-Gaussian unitaries that are just exponentiation of kappa, or in this case larger than 2, like 4, Majorana. For example, the swap gate can be written as a polynomial of kappa. Majorana. And why studying non-Gaussian circuits and states? Because they model interacting physics. If we want interaction, we should have these gates that are not quadratic in Majorana operators. And also, this class of gates is universal for quantum computation. And it's known that until t equal log n, efficient classical simulation for these magic circuits is possible, where t is the number on magic gates, and above log n is no longer possible. So a question is, what about their learnability? Can we learn these states with few magic gates? Okay, we show that, a spoiler, this is the same. We show that it's easy to learn these states for up to log n, and no longer for larger than log n t gates. And this also gives a new form of complexity. Now we can really tell that more than log n magic gate states are hard because they are hard to learn. Okay. And at the basic, at the center of our learning algorithm, there is a theorem that we believe to be also fundamental interest outside learning. That is the magic compression theorem. We show that a state prepared like this can be rewritten in this form, where this is a Gaussian unitary and this is a non-Gaussian unitary supported only on T qubits. And basically, you can move the magic wherever you want. And analogous theorem holds for Clifford plus T. And the implications are, for example, a more efficient compilation strategy for non-Gaussian circuits, or also a crucial idea for learning. Because why crucial idea for learning? Let's see this in more detail. Let's assume that we have an unknown T-dot Gaussian state. And let's imagine that we can learn this Gaussian unitary G. If we learn it, then we can undo this G. And then we can do full state tomography on these first T qubits. And if T is small, we will have efficient tomography. And if T is log n, we will have efficient tomography. OK. And we can learn actually this G. And by manipulating carefully the correlation matrix of the unknown T-dot Gaussian state. And so for T equal log n, for magic gates, we show that T-dot Gaussian states can be learned efficiently. But what if larger than log n? We show that this is no longer possible up to crypto assumption, like ring LWA cannot be solved by quantum computing in sub-exp time. And so a learning algorithm would also imply a breakthrough in cryptography for this class of states. And also, we have an experimentally feasible protocol, noise robust. And we extend our algorithm to all T-compressible states that are states of this form. And for example, ground states of impurity models that are interesting models in physics. And we also provide an efficient testing algorithm for such states. OK, so the summary, we have seen optimal trace unbound for Gaussian states and efficient learning, hardness for testing in the general scenario, but efficient learning for low-rank states, and magic compression theorem, and efficient learning of T-compressible states. And we have seen that log n marks a critical threshold for learnability, which also gives a new form of complexity. And the open questions can be learning T-dot Gaussian unitaries. T equals 0 also is already solved in this paper. And also here holds a compression theorem. If you are able to invert this unitary, then you can do full process tomography here and learn the unitary. OK, then another problem are agnostic tomography that you will hear more tomorrow for some class of states, and testing Gaussian unitaries, or also optimal learning of free fermions. Here I have more things to say, but I will leave for later. OK, thank you so much for your attention.
Yeah, thanks for the great talk. About your the robustness of your Gaussian state learning algorithm, how much noise can you tolerate? Like, can you tolerate, like, like, say, given a state that's like epsilon far away from a Gaussian state, can you find the closest Gaussian state, like epsilon minus tau or something?
OK, for Gaussian state, we have two different notions of closeness. If we have the prior assumption that the state is epsilon square close in relative entropy to be from a set of Gaussian state, then we can guarantee efficient learning. Or also we have trace distance closeness, but with a linear in the number of qubits at the denominator, epsilon over n. Yeah. So yeah, it would be interesting as an open question to relax more this assumption.
And can you say a little bit more about what you mean by simple measurements? You say several times simple.
Yeah. All the measurements that we consider are free fermionic. I mean, can adjust Gaussian time evolution. Gaussian evolution. And you can Gaussian states you can learn also via just Pauli measurement by paying a linear in the number of qubits or modes overhead. Yeah. So.
Sweet. Over here. Thank you for the talk. I was curious about one slide that you had that said wasn't like efficient measures for magic, I guess. Because I was interested if you had thought about like sort of these like finite phase space methods for fermionic systems, or like looking at like the cumulants of these states, since these like Gaussian distributions are like invariant under convolution, or like Wick's theorem type arguments.
That's okay, an interesting question. Here, basically, this statement that there are no efficient to estimate measure of non-Gaussianity, it's basically implied by the hardness of testing, possibly mixed Gaussian states.
Oh,
okay?
I see.
And but efficient measure of Gaussianity can still exist for pure states.
I see. Okay, it's the ranked argument. That's
Yes,
I
yes,
see.
yes, yes.
Thank you.
Thanks for a nice talk. I'm here. So I have a question about, you talked about improved sample complexity in comparison to two papers. So usually tomographic sample complexity is square. So what were they doing there whenever they were getting?
Okay, that's an interesting question and very important. Okay, basically we have shown, basically at the heart of the sample complexity analysis, there is these types of inequality, trace distance between Gaussian states and their correlation matrices. Previous works didn't have such tight inequality, they had a square root here. We improve this basically inequality by removing the square root, and so we can improve the epsilon to the 4 with epsilon square. Yes.
Hello, sorry. First, can I look at the definition for the correlation matrix for a second?
Sure. It's expectation value of two-body Majorana.
Okay, I see. Thank you. Another question is this whole research only for spin 1/2, or is it generalizable for like arbitrary spin?
Okay. Okay, you mean spinless fermions and spin full fermions?
Like all other spins. It's like because I just don't know which specific spins you're talking about. Or is it like?
I guess. Okay, basically we consider here spinless fermions in our paper for simplicity, but probably there is a easy way to map spin full fermion into spinless fermions by like doubling the number of modes, and there is a standard argument in the literature that allows to do that.
Okay, thank you for reminding me the result.
Hello, thanks for the very nice talk. I have a question about, let's say, the implementation of your results. I mean, do you know how we could, I don't know, like learn this free fermion part G that we somehow need to undo?
That's a very good question. Yeah, basically, I didn't say how to learn specifically. We just need to estimate the correlation matrix, diagonalize it, and we will have the diagonalizer orthogonal matrix. If this orthogonal matrix, we can construct the Gaussian unitary. Yeah, basically, you estimate the correlation matrix, you put into so-called normal form, you take the orthogonal matrix, and you add the Gaussian unitary. We can prove that this Gaussian unitary basically corresponds to this G.
Okay, thank you.
All right, let's thank the speaker again.